Hello guys, welcome to my YouTube channel. Today in this video I'm just going to make you learn the encoder, decoder, multiplexer and demultiplexer. So this video is consisted of two parts, that is lab 10 and the second one is lab 11. So first in this lab 10 we will learn encoder, decoder, multiplexers and demultiplexers, and in the second part of this video we will learn what are flip-flops, D flip-flops and SR flip-flops and JK flip-flops. So let's start the lab number 10. So the objective of this lab is how to implement the circuit using the universal gate on breadboard and working on Proteus, implementing and comparing the results of encoders and multiplexers using the universal gates. So here you can see that a multiplexer is can be 4 cross 1, means that in the multiples of 2. So by having the selection lines that are also in the multiples of 2, for example, if I have the two selection lines, then the input will be of 2 raised to power 2, means that 4. If I have 4 selection lines, then means 2 raised to power 4, then the 16 selection lines will be appeared here. So there will be the total number of 16 selection lines, 16 inputs for the 4 selection lines, and the output will be 1. This is the simple that is a block diagram for the multiplexer, and the demultiplexer is a reverse of this, and there is also an enabled input attached to the multiplexer in order to operate it with only the single input, that is the enable. For example, if the enable is 1, then all the inputs will be worked together to give the output, but if the enable is 0, then these selection lines can do nothing because the enable is 0. Actually, this is the main power switch that is used to run the multiplexer. So demultiplexer is the reverse of this. In the demultiplexer there is one input, and the total of the 4 outputs, means the 4 cross 1 DEMUX is the 4 outputs and the 1 input and the 2 selection lines and enable as well. And then there comes the general encoder, in which you can see that there are the total number of 2 raised to power n inputs, and the n outputs are there. And if we take decoder, then the n inputs will be here and the 2 raised to power n outputs will be there. So this is the structure, this is the table, truth table for the decoder, that is 2 cross 4, in which you can see that 0 0 0 1 1 1 and 1 0, and the output of there are the 4 outputs, 2 inputs, means that 2 raised to power 2 is 4. So but if we apply 0 0, the output will be 1, and if we apply 0 1, the output at the 2 of 1 will be appeared. So let's simulate it in the Proteus to make a better understanding how does the decoder works. So here is the enable input that is mainly working as a power switch for this entire circuit, and here we'll see that I have just turned on the entire circuit, and then actually it's not working. So we will see that whether we have applied here. So here you can see that the 0 is applied, so we will apply it minimum 5 volts to operate it properly. And here we also see that there is a 0 volt, so I am giving it 5 volts. So now the circuit will operate properly. And here I have also attached the resistors at the output of this button to give the voltage drop across these gates. So now here is the simulation. Here you can see that now it's working properly. So the first column of the table was that if I apply the input A is equals to 0 and B is equals to 0, then the output then the 1 at output 1 will be appeared, but if 0 1, then the 1 at output 2 will be appear. So here you will see that the 0 0, data 1 and data 2, I am applying 0 and 0, so the output 1 is appearing at gate 1. So now I will apply 0 1, and you will see that the output at this will be appear. So here, according to the table, if you can see that I'm just going to apply the 1 and 1 at the both terminals, then the output at this will be appear. So now we will go towards the working of encoder, that is 4 cross 2. So here let me make you show that there are the total number of the inputs that are A, B, C and D, and the outputs of 2 are here, and we will apply the 1 at A and then we will see that the output of 0 0 will be appeared, and then if I apply 1 at here, the output of 0 1 will be appeared. Means that this is the reverse of the encoders. The table is same, just like shown. So here you will see that let's simulate it. This is the encoder, and I have turned on the enable. This is the enable, and here it's working properly. And okay, so if you can see that I'm applying 1 at input 1, so the 0 0 is appearing. But if I'm going to apply the 1 at here, then you can see that 1 at output 1 will be appeared. But if I will apply 1 at here, then you will see that the output at this second output 1 will be appeared. So here you will see that the 1 will be appeared here, and then last but not the least, the fourth input is here, and both the outputs at 1 1 are appearing according to the table. Here you can see that. So now we will move towards the multiplexers, and here you will see that the multiplexers is this. There are the total number of here you can see that A, B, C, D, and the 4 inputs, the 2 selection lines, and the 1 output. So the data at output in all the situations will be appeared if it will follow the table in exact way. For example, if I'm going to apply the selection both the zeros at the selection lines, then the data at A will be appeared, and if I'm going to apply the the 1 at only selection 2 lines, the data at B lines will be appeared. So let's simulate it in the Proteus, and here you'll see that this is the structure for MUX, and these are the circuits. These are the only this is the one input that I have applied 5 volts here, and just like the previous one circuit, this is the A, B, C, and D. So first, if I will so these are the selection lines, selection 1, selection 2. So according to the table, first I am going to apply the data at A, and then selection lines will be 0. So here you will see that the output 1 is appeared. So next I am going to apply the data at B 1. Then you will see that after applying 0 1, the output will be appeared. So and after applying C at 1 at C, so here you will see that the higher logic state for 1 will be appeared at the output when 1 0 will be given, and the D data will only be transferred in the situation when both the inputs of selection lines will be at 1 logic state. This is the multiplexer, and now we will move on towards the demultiplexer. Demultiplexer is the reverse of multiplexer. They are the 2 selection lines, and the outputs of 4 are here, and you will see that the selection lines is 0 0, and the data of will be applied to the data will be appeared at the output. But if I will apply 0 and 1 and the selection 1 and 2 respectively, the data 2 will be appeared. So here you will see that this is the data that is just an enable for the decoder. Here you will see that the decoder and the DEMUX structure is same, but only the names are changed. Here you can see that this is enabler, and only difference is the data and the selection lines. So first run it, and here we show you that the data will be applied in all the situations. In order to deliver it to the particular gate, I will let you know how does it work properly, and just turn off all the knobs, and here we'll see that the data at 1 will be appearing. If I apply 0 and 1 at the selection 1 and selection 2 respectively, then the output at this terminal will be delivered, that is the B. So here you will see that the output is appearing here. But if I apply 1 0 at the selection 1 and selection 2 respectively, you will see that this is appearing as 1. But if I apply at the both terminals, then the output 1 will be delivered to the 4th gate, that is D out. So now we will learn about the D flip-flops. So what is flip-flop? Flip-flop is the memory element that is used to store the 1-bit value. So flip-flop just generally works on the clocks. Here the clock is provided to the both inputs of the NAND gates, and then you will see that these 2 NAND gates are connected in such a way that they will store a 0 or a 1. So in D flip-flop, the structure is just like this, that this is a NAND gate flip-flop, and here you can see that The two NAND gates are one output of the NAND gate is connected to the input of the second, and the input of the second is connected to the output of the first. So this is Q and this is Q dash, because when this LED is turned on, this will be automatically turned off, and this will be on, and then this will be turned on. So I have applied the 5 volt here, and when I just press this knob, you will see that the inputs at both terminals are 1, then the 0 will be transferred to there, and then the 1 will be transferred here. So 1, and then you can see that this is also 1, then 1 1, then output of 0 will be appeared here. And so here you can see that, I'm sorry, so here you can see that the output will be 0 at here at when I press the button here, because this is also 1 and this also 1 is delivered to here, and in turns there is a NAND gate and NOT gate is attached at the output of the NAND gate, then this will convert it the 1 into 0. And then you can see that if I apply here, this is already 1, and then if I apply here 1, and then the 0 will be appeared at this output, and then in turns the 1 will be given, means that here is 1 and here is 0, sorry, here is 0 1 and here is 0. So the opposite polarities are here, and then you will see that this will produce the memory that is being saved here. And for example, if I am going to just simulate it, then you will see that after pressing this button, the logic state of 1 is appearing here, and then the logic state of 1 is also appearing here, but it is a clock. So the clock element just changes the value of 0 and 1. Here you can see that the value is changing with the time, and the 1 is appearing here and 0 is appearing here. But if I am again turning off the knob, then you will see that the LED will be turned on in Q dash section, because now both are 1 and this will become 0, and now the states are changing accordingly. Here I will again apply 1, then you will see that the transition is transferred to the Q, because again by applying 1, and here you can see that the clock is changing with the time with the frequency of 1 Hertz, and then 1 1 will be the 1 here, and then again the 1 0 will be the 1 here, and then again you will see that the Q dash output will be the 1 logic state. And here you will see that after again opening the button, the Q dash LED will turn on, and then the Q LED will be turned off. Again pressing here, you will see that. So this is the working of D flip-flop, and next we will move on towards the working of JK flip-flops. So here is the entire structure for the JK flip-flop. It is similar to the D flip-flop, but here is the input at the D2, and this input is connecting with the 3 terminals NAND gate, and then you will see that the resistors are just used to ground the input, and the voltage drop will be appeared at the NAND gate, 1 terminal out of 3, and the clock is just provided to the each of the AND gate that is working as an enabler. So here we go. So it has the 2 inputs. You can see that the one is turning off and on with the frequency of this AND gates, with the frequency of this clock that we are providing of 1 Hertz, and then again turning the knob off for this Q dash. You will see that this will off, and for example, if I'm going to turn on this one, then you will surely see that this will be turned off, and the blue LED will be turned off at D2. So if I turn off both the knobs, then you will see that the blue LED is turned on for D2. So this is the temporary storage of the memory, and here you can see that I have just applied the clock at the input for the AND gate 1, and this has temporarily stored the data at of 1 at D1, and you will see that it will not change. But if I'm going to just press the knob for D2, you will see that the data is shifted to D2, and then if I again press the data entry for D1, then the D1 will be turned on. So this is the working of JK flip-flops. Now we will move towards the SR latch, that is a simple. Here you can see that this is the Q and Q dash, and this is a simple structure. Actually JK flip-flop is the derivative of SR latch, and you can see that it is working in the same way as the previous one. This is the white LED that we used, and you can see that now it has stored data at D1, and you can see that I have now turned off the knob. Then the one at D1 is saved, means that the Q dash data is saved. And now to shift the data to the Q, we can just turn on the knob at this. So it has just took 1 second to shift the data, just because of the knob frequency. For example, if I am going to increase the frequency, let's suppose 3.4 Hertz, so you will see that it will transfer the data in a faster way. So here you can see that it took a little bit of the time to transfer the logic state from Q to Q dash, or Q dash to Q. So this is just because of the delay in the frequency, as I have applied 400 millihertz, means that approximately a half of the second. So it is working properly. To transfer the data, we are using just two knobs at the inputs. And now we will move on towards the working of the master slave flip-flop, and then we will see that how does it work in the Quartus software using the Verilog code on the base on the gate level implementation. This is the master slave flip-flop. Actually the two flip-flops, here you can see that this is the one flip-flop and this is the second. So this will be considered as the master flip-flop, and the this flip-flop will be considered as the slave flip-flop, because the slave flip-flop is following the master flip-flop, because the input of the slave flip-flop is the output of the master flip-flop. But the only difference is here that the AND gate input is applied to one of the input terminals of the NAND gates that are used here. And if I will simulate it, here you will see that the only one button is used to shift the logic state from D1 to D2 and D2 to D1, and then you can see that the logic state is shifted. When I press this button, the logic state is shifted from D2 to D1 and then D1 to D2. Here you can see that only one button is using to control the inputs and the output. For example, here you can see that there are some drawbacks, that we use two buttons here to change the transition from one logic state to the other, and it is the master slave flip-flop is more efficient, because it only uses one button to shift the or to store the data from 1 to second and second to 1. So now we will see that how it's working in a Verilog HDL code. And here you can see that this is the MUX code. These are the total number of the inputs and the outputs that we are providing, and the output is only F, because the 4 cross 1 MUX. The input are A, B, C, D, and the two selection lines, and one is enabled, and the wire is just that are not defined in input and output. These are called as wires. So this is important to declare the wires, because these are the internally structures, and not declaring the wire can collapse the circuit. So here it is generating a parallel circuit, so the wire declaration of the wire is necessary, and the NOT gate is attached to the selection. The output for after the NOT gate is NOT door SL, and the input is selection, and means that the selection one line after the NOT gate becomes NOT of SL. So these are the inputs for the AND gates: enabler 1, enable 2, enable 3, and enable 4, and then the operations at A, NOT of selection, and NOT of selection 2, and enable is just working like that. So we will first locate the node in RTL view to see that the circuit is properly made or not at the base level gate level implementation. So here you can see that this is the circuit that we were wanting. This is the two selection line and the A, B, C, D inputs, only the one output, that is F. So this is working properly, and if I see towards the MUX, that is a DEMUX code, and you have to just declare the file as you have renamed the file, that there are the total number of the outputs that are 1, 2, 3 and 4, and the input is only 1, and the 2 selection lines and enable line that are working as an input. So here is the RTL view for this. We are just locating the node, and here you will see that the RTL view for this circuit, this the code will be the same like that. Here you can see that the total outputs are 4 and the input is 1. It is the 1 cross 4 DEMUX, and the enabler and the selection two selection lines. And now we will move towards the next code, that is of encoder. You are just reading the file as I've explained in the previous one. And encoder, and the total number of the inputs are enable ABCD, so the outputs will be 2, that is F1 and F, and the wire D1 and D2, that will be the internally wired connections that I have already shown the circuit to you in the first section of this video, that is the lab 10. This is the lab 11, and this is the wire, and I am just going to assign the D1 is equals to C, and this is the OR gate, and C or B, and B or D, and this is the AND gate, and this is the enabler of AND gate with D2, that is assigning to D1. So now we will see that the locating the node in RTL view. Then you will see that if the you can also see that if the circuit is properly made, that we have made in Proteus, then you can imagine that this circuit is working properly. So here you will see that the total number of the inputs are 4, and this is the enabler of for the AND gates, and then you will see that the 2 inputs. So this is the exact structure that we were wanting. And the last but not the least is decoders. I have the total number of the 2 inputs but the 4 outputs with an enabler input. Now we will locate it in the RTL viewer, and here you will surely see that the total number of the inputs will be 2 and the outputs will be 4, as we were expecting. This is the NOT gate, don't to be confused with these teeny circles. So this is an enabler, and here you can see that the AND gates outputs are just appearing like that. So this was the video for today. I hope that you learned whatever I was wanting to deliver to you. If you really enjoy this video, don't forget to subscribe my channel, and if there is any query about this, please don't forget to comment me in the comment section.